All right, hi everybody. So in this video, I'm going to go over one of the basics. And this is really a notation basic that's used a lot of times in CFD, and it's called index notation. And this is often used in conjunction with or instead of vector notation. So I'm going to write both of these forms next to each other so you can kind of start to get a sense of what it looks like. And really the benefit of index notation, in my opinion, is it allows us to write equations kind of in a sort of shorthand. So we can take our Navier-Stokes equations, which if you write in explicit Cartesian vector notation, you're familiar with seeing, three explicit equations, one for each component of those conservation of momentum equations. So you have one in the x, y, and z directions. On the other hand, index notation allows us to write it just as one equation where we're kind of using this shorthand to imply an equation in all three directions. I also find that it's useful for not having to remember really helpful and common vector identities. And so I hope you find it as useful and as helpful as I do. Okay, so just to make some comparisons to start, I'm going to keep index notation on this side, and then I'm going to put vector notation on this side, just so we can see A to B, what we're looking at. So in vector notation, if we have a scalar, it's just going to look like this. So any letter of your choosing. In index notation, it's exactly the same. No changes whatsoever. Okay, a vector, I tend to write with a little vector arrow over the top. In a textbook, this might be a bolded symbol or perhaps a symbol with a line underneath are all common ways to write vectors. In index notation, you're going to have an A, or your variable, with a subscript I. And I'll go into a little more detail about what that I means in just a second. And then also we can have tensors. So tensors I'll generally denote with a capital letter and then two underlines underneath. And the index notation here is the letter again, or the symbol, and then here you see we have two subscripted letters, an I and a J this time. So just to kind of revisit what each of these quantities are in practice, a scalar is a magnitude, essentially, that does not change with any rotation of axis. So a scalar is the same scalar no matter what frame of reference we're in or what orientation we're looking at it. A vector, on the other hand, essentially takes a scalar and associates it with a direction. Okay, so now it depends on our frame of reference or the rotation. A vector will change. Kind of the extension of that analogy, a tensor, which you can also think of as a matrix if you have a second rank tensor, associates a vector with a direction. Now, if you're not used to formerly hearing something called a tensor, you're actually probably familiar with tensors already. One that you're probably used to seeing is stress. So stress is a tensor. And a fun one that many people don't actually realize is a tensor, but actually is the diffusion coefficient. Is properly a tensor. We usually approximate it as a scalar. That's just a fun little fact there. And then, so this is the nuts and bolts. So this is technically a second order tensor. And you can also have higher order tensors. So I, J, K. This is a third order tensor. And generally, in everything that we're going to be talking about, 3 orders is plenty for us, but strictly speaking, in terms of math, you can have any number order of tensors. You can increase your dimension however you like or need, physically speaking. Okay, so now I'm going to go into a little more detail. What do these letters actually mean? So these letters will fall into one of two categories. You can have a free index. So this means that the letter appears only once. It also means that this same letter needs to be the free index on every term that is added together. Or in other words, you have to use the same letter as your free index for terms that are added together. Okay? And one example of that would be if you have, say you have two vectors that you want to add together. So if you had A plus B, and this is in vector notation, if you did this component by component, your vector would look like A1 plus B1, A2 plus B2, and then A3 plus B3. And so the way you'd write this in index notation is you're essentially you want to add together each of your scalars in that directional component. So you would have AI plus BI. And here, one last little note about the free index. The free index, and all indices really, implies I equals 1, 2, and 3. And you can really see that in this example here, where I have AI plus BI, and then if you look at this expanded form here, I've got A1 plus B1, A2 plus B2, A3 plus B3. So essentially I have 3 distinct equations for each of the components of this resultant vector. Okay. Okay. All right, so a few more things on the free index. Any free index you have, you need to maintain consistent nomenclature from term to term to term, but that doesn't mean you can only have one. So you can have more than one. A good example of this is if you have a tensor, for example, or all of the terms in your equation are tensor valued quantities, then you would have 2 free indices. So for example, Aij plus Bji is the same thing as writing the tensor A is added to the tensor B transpose. All right. Another note on free indices is the number of free indices that you have gives what's called its rank. So for example, a scalar, is rank 0 because it has no free indices, so rank 0. AI, which is a vector, is rank 1, has 1 free index. Aij is a second order tensor or rank 2 tensor. And then same thing with rank 3 tensor. So we've got 3 free indices here, and this is rank 3. Right? Okay. Another important thing on rank here is you can only sum together quantities that have the same rank. So this one is, I think really obvious in vector notation. You would never expect that you can add a scalar to a vector or a vector to a tensor or a tensor to a scalar. I think it gets a little more trickier to spot that when you move to index notation for some people. So this is actually one of the ways that I really like to check I don't have a mistake in my work when I'm using index notation. So one good check is if I have an equation with several terms added together and I'm simplifying those terms, if I end up with different ranks among those terms, I know I've got a problem somewhere. So that's a good sanity check. Okay. Finally, the convention for anything with rank 2 or higher is that the first index responds to the row, if we're talking about like a matrix, for example, and the second index corresponds to the column. So for example, if we have Aij, we would have a tensor or a matrix that looks like A11, A12, A13. So here I've got 1 for each of these because it's all the same row. And then 21, A31, A22, A32, A23, and then A33. So here you'll see our first index is 1, 1, 1 for the first row, 2, 2, 2 for the second row, 3, 3, 3 for the third row, and then our second component is 1 for our first column, 2 for our second column, and 3 for our third column. Okay, great. So our next thing about indices is dummy indices. So dummy indices, in contrast with free indices, are indices that are repeated in the term. So a dummy index, sometimes also called a repeated index, is repeated, but only twice in the same term. And when this happens, what it's doing is it's implying a summation. And this is all kind of abstract. So I think the best and simplest illustration of how dummy indices work is if we look at the dot product. So if we go to our normal vector notation that we're all comfortable with using, if we have A dotted with B, we know that this is going to give us a scalar, right? And what this looks like is we have A1, B1 plus A2, B2 plus A3, B3, right? Okay, so the way we would write this in index notation is we have our A and our B, and now all we're going to do is use the same index on both of these, and it can be any letter that you want. So let's say it's K. All right, and so what this implies is the following. You can throw the summation sign out front and say that your dummy index, K in this case, goes from 1 to 3. All right, so we don't, in index notation, we don't actually write this summation sign. We're just saying this is our shorthand, and if there's a repeated index, this is what we mean. If you ever get lost when you're starting out with this, absolutely feel free to just write these summation signs in when you have a dummy or a repeated index as you're getting used to it. All right, and so if you write this out, we get the exact same thing as we had before. All right, so that's great. So we took this whole equation and we are just writing it like this. Another thing that's really nice to note here is that our dot product takes two vectors. So these are both rank 1, right? Because they have, they each have an index, so rank 1, and we're bringing it down to a scalar, which is rank 0. So anytime you have a repeated index, you're going to bring your rank down by 1. All right, so from here we went from 2 rank 1 items to rank 0. Okay. So at this point, it's a good kind of place to make note of 2 really useful tensors, especially when you're using index notation. The first one is called the Kronecker delta. So this is a rank 2 tensor written with a lowercase delta and then 2 indices, I and j. And this is defined as being equal to 1 if I is equal to j, and 0 if it's not. All right, and so if you write this out, you might recognize this tensor as a familiar structure. So this is essentially our identity matrix, right? So that's handy. That's going to come up a whole lot. And then the other one that we have is the alternating unit tensor. So this one is actually a rank 3 tensor. It's denoted with an epsilon, and then I, j, and k are its free indices. And this one is defined a little bit more interestingly. So it is 1 if I, j, and k are equal to one of the following combinations. So we've got 1, 2, 3, 2, 3, 1, or 3, 1, 2. It's 0 if any I, j, or k are duplicated. And so by that I mean 1, 1, 3, 2, 1, 2, anything like that. So we have 2 indices that are 1, 2 that are 2, so that means it would be 0. And then this is -1 if I, j, and k are any of the following combinations: 1, 3, 2, 2, 1, 3, or 3, 2, 1. All right, and you might be thinking to yourself, wow, that's like a lot to remember, right? All these different combinations mean different things. It's actually not so bad. There's a nice little trick to remember which one you'll have here. So if you write down 1, 2, and 3 in a triangle like this, all you need to remember is that if the order of your indices go clockwise, then it's a +1. And if they go counterclockwise, it's a -1. And then otherwise, it's 0. All right, and so this one is really important for defining the cross product, which I'll do in just a second. All right, and at this point, I just want to note, and this is a really important thing to remember, when we write things in index notation, you'll notice that by putting the index on our terms, here we're referring essentially to each individual component of a vector or a tensor, for example. So epsilon ijk, epsilon itself is a rank 3 tensor, but for every epsilon ijk, we're just referring to one individual component. So one of the 27 pieces that make up the whole tensor, we're just referring to one at a time. So basically, when we're looking at index notation, all we're talking about is the scalar pieces that make up higher dimensional mathematical structures. All right, and that makes things really simple for the math. So when we write it in this way, since everything is a scalar, we really only have a definition for addition and subtraction and multiplication and division. And so everything else that you're used to seeing in vector valued expressions like curls and dot products and divergence and gradients, we're going to be able to write those in ways that only leverage multiplication, division, addition, and subtraction. And I'll show you that right now. So to go over just a few very common operations that happen. The first one is multiplication of a vector with a scalar. So in vector notation, we have something like this. So a scalar A times a vector B in index notation, this one's pretty straightforward. Our A stays the same and our B just gets an index. Again, this is a free index. It can be any letter, symbol, whatever we choose. We just have to keep it that same thing for anything we're adding it together. Okay, next one is the dot product or the scalar product or the inner product. It has a few different names. So this one's going to look like, as I already wrote before, we have A dotted with B, and this just becomes AI, BI. Simple as that. And again, this implies a summation again from I equals 1 to 3, AI, BI. All right? So like I said, we don't actually write this whole summation out. Our shorthand is that this repeated index implies this thing right here. Okay, the scalar product of two tensors, sometimes this is called a double contraction. We would have Aij and Bji. All right, and so you'll notice here we have two repeated indices. So we have a j and a j, and an I, and this is going to give us scalar in the end. All right, in vector notation, this is often written as, so I did the index one first, sorry. So we've got our tensor A double dotted with our tensor B. All right, next one we can have is a tensor product. This is also called a dyadic product of two vectors. So this is taking two vectors and making a tensor of them. There's two ways to write this. You might see A and B, where these are both vectors. Notice there's no dot in between them. I'm not as big of a fan of this notation. I think it can be a little bit misleading what you actually mean by that, where this is a tensor C. I prefer this notation where you have the cross symbol with a circle around it. So this is very clear to me that we're doing a tensor cross product. And so what these both mean is we have AI and then BJ. So we end up with a tensor Cij. So we have two free indices here, which means that this operation is going to give us a rank 2 tensor. Okay, we can also have a tensor product of two tensors. So we're just contracting out one index. So we're having an operation that has two second order tensors and gives us a third second order tensor afterwards. So this is often written with our dot as so. And all of these are second order tensors here. And the way we'd write this is we have Aij and then Bjk. And so you'll notice here that I'm going to repeat this index, these indices that are right next to each other, right? This would not be the same thing as Aij, Bkj, right? This is not the same thing. Okay. Okay, then we can also have a vector product of a tensor and a vector. So if we have the vector A acting upon the tensor B, this is going to give us a vector, and we can see that by writing this out in index notation. So we have AI and then Bij. So you'll notice we have a dot here, which means that I'm going to repeat this index that's on A as the first index in B, so I and I. And so our resultant quantity that we have here, let's call it C, is just C sub j. So that means we have a vector. All right. Now, we also have the cross product. And this is the one that uses that alternating unit tensor that I explained a little earlier. So if we have our cross product A cross C, then we're used to writing probably many of you are used to writing this as a determinant where you have I hat, J hat, k hat, and then your components A1, A2, A3, and then C1, C2, C3. And this is a negative j hat, I believe. And so this is how we're used to writing it in vector notation. This is kind of our way we remember how to do this operation. But in index notation, we write this as epsilon ijk a j c k. And I want you to notice a few things here. So we always have our alternating unit tensor out front, and I'm always going to give it ijk. Technically, you can give it whatever letters that you want, but the important thing to note here is that the last two letters are going to be the free indices on the vectors that you're doing the cross product with. And you're going to put those vectors in exactly the same order here. So the first one we do is A, and then the second one is C. And you'll notice that the index on A is this second one here, so J, and then the third one goes to our second vector. All right, and so that's how we're going to organize this. And if you use the rule of your epsilon rank 3 tensor, all you need to really remember is that if you go clockwise around the 1, 2, 3 circle, you get a positive 1. If you go counterclockwise, it's a negative 1. And then anytime I, j, or k are repeated, it's 0. All right, so you don't have to remember any of this anymore. Just remember clockwise, positive 1, counterclockwise, negative 1, and you're golden. Okay. Let's do a few calculus-related operations. So the gradient is written as partial xi. So this is something that will increase the rank of your whatever you're acting upon. So if you take the gradient of a scalar, for example, you get a vector in as your result. If you take the gradient of a vector, you get a tensor. So it always adds rank. Okay, so that's good. And also, you are going to always have the derivative be the last index. So what I mean by that is if we have the gradient of a vector A, I'm going to write this as partial AI partial xj, where I is going to be my rows and j is going to be my columns. Okay. The next one that we have is divergence. So this is usually, we have our gradient operator and then a dot product. All right, and so you can think of this as actually kind of like two separate steps. So if we have the gradient, which gives us a vector essentially, and then dotted with another vector, that means we're gonna contract these two things into a scalar. So I can write this as, if I say I have partial xk, so this is my gradient operator, which is technically a vector, and I'm going to dot it with another vector, so that means I need the free index, or the index, to be repeated in this case, so I would have ak. And so when I do this, this is implying our summation again, from k equals 1 to 3. And so if you recall, your divergence operator always gives you partial a1, partial x1, plus partial a2, partial x2, plus partial a3, partial x3, right? Okay. The next operator, I need more space for. Okay. So the next thing that we have is the curl. So this one is the gradient operator crossed with something, let's say a vector. All right. And again, we can essentially use all the building pieces that we've already talked about. So we know what the gradient operator looks like, and we know how to write a cross product. So I'm essentially just going to use those two pieces and put it together, and that's how we do index notation. So when we do a cross product, we have our alternating unit tensor. I'm just going to use IJK. It's kind of habit. Most people do that. But again, you can use whatever letters you like. All right, so the next piece to this puzzle here when we do a cross product is we're going to do our first vector, and we're going to give it the free index of j. Okay, so I've got partial xj, and then a, we're going to give it the free index k. And that is it. And so you'll see here that we have j as a dummy index and k as a dummy index, which means that we get a vector c back where the free index is I, the one left over. All right. The last one operator that I have is the Laplacian, and we'll say of a vector here, where this can be written as the divergence of the gradient of A. Right? So this operation here, we're taking A and we're adding an index to it. So we're making this a tensor, and then by taking the divergence of that, we're taking away a rank and giving back a vector. All right, and so I'm just going to write this in the same way using my pieces that I've done before. And so I'm going to work my way from the inside out. So gradient A, I'm going to say, is partial aj partial xi. And then we're doing a dot product, so this vector has to have the same index as our our first index here. So I've got partial xi. All right. Okay. And you might be thinking, well, how do I know I give this operator an I instead of a j? So the way I want you to think about that is look at how this appears. This one is first. So I'm going to say this is partial xi, and this is a sub j. So this is my first index. It's kind of hard to see that when you write it, in the traditional way. And so my operator here is going to be another xi. Okay, and so what we have here is, again, a vector where we're summing over this repeated I index. And so if I write this out explicitly, you get the standard Laplacian that you're probably used to seeing. So the second derivative with respect to x1 plus the second derivative with respect to x2 plus the second derivative, one with respect to x3. And this is a vector, right? So you'd have the same thing for each of the other directions. So now we're operating on the second component. And then finally, we're going to operate on the third component. And then that's it. All right, so this is probably a good example of how you can see that this shorthand is a whole lot less writing to imply all of this. All right. Okay, in index notation, we can, since you remember my comment about we're essentially referring to these scalar components of higher order mathematical constructs. So an important rule that we want to remember from calculus is our product rule. So if we have the following expression, so we've got a derivative times or taking on a tensor a tensor product of two vectors, we can write this as two added quantities using the product rule. So I can write this as AI partial bj partial xk plus partial AI partial xk times bj, right? So that's just the product rule. That's a handy one to have. And that's pretty much it.